Okay, so let's start. So what is this talk about? So this talk will be about solving initial value problems for ODEs of the form, of the following form. So we have the time derivative of y is equal to some right-hand side function f, and there's an initial value y0 is given for some d-variate function f. And what we want to do is we want to compute the solution y. So the first question is what we actually mean by computing y. So one possible interpretation would be to just show some non-uniform results, so that if f and y0 are computable, that the solution y will also be computable. But here, what we want to do is thinking more about, so the way of thinking here is more that we will, so the definition of an actual ODE solver that gets the right-hand side function f as an input and which will somehow compute the solution function. So the function should be an input. And this can, of course, be made formal by using representations for function spaces. But in this talk, I will mostly not explicitly talk about represented spaces and so on, but I will just state all the information so all the information that I will make explicit all the information that the algorithm needs about the function, but not call it a represented space and so on. Okay, so let's start it. So what I forgot to say is, so in this talk, so this is the most general case, but in this talk I will only consider the case where f is analytic. So the motivation behind looking at analytic functions comes from some classical results in real computability and complexity theory. So there are some results that say that if the right-hand side function f is polynomial time computable, then, well, the solution doesn't even have to be unique. And if it's not unique, then all solutions can be non-computable. On the other hand, if there is a unique solution, then the solution will always be computable, but the complexity can be unbounded. So, so if it's Lipschitz continuous, if the right-hand side function is Lipschitz continuous, we know that we know by the Picard-Lindelöf theorem that there will always be a unique solution, and this solution will always be computable, and it will always be computable in p-space by using something simple like the Euler rule. And actually, this result is optimal in a certain sense. So it has been shown that if we only know that f is Lipschitz continuous, then the right-hand side function, then the solution function can actually be p-space hard. So this is why we want to restrict the functions we look at, and we want to look at analytic functions, because for analytic functions we can do better. Okay. And now I will start the whiteboard part of this talk. So let me insert a new slide and hope that this works. So actually, so what is the problem we look at? So the problem is analytic ODE solving. And so let me first specify the problem. So consider the initial value problem given by the following ODE system. So we now have a system of ODEs where y dot k of t is given by some function f that depends on this vector d-dimensional. And we are given some initial value at 0. And we also restrict to some compact domain. So here we restrict to some polydisk A, B, D, and such that each fk is analytic on this polydisk. And there is a solution Y defined on some interval mapping into this polydisk. And the question is how to compute Y. Okay, and so we can, so all the results I will show today will hold in this general setting with some slight modifications. But for the talk, I want to make some simplifications. So first, I just want to look at one-dimensional functions. So this is just a one-dimensional function. And I also only want to look at initial value 0. And we replace this interval by 0, 1. And also here. Everything by 0, 1. Okay. So is this kind of whiteboard presentation, is it working so far? Is it okay?
Yes.
Yes,
Okay.
yes, everything working.
Okay. Then I will go on. So, and I will split this problem in 2 parts. So first, the first thing I will do is how to compute a local solution on some small interval, and then how to extend this local solution to a bigger interval. Okay, need to make a new slide. Okay, so let's first start with what I mean by computing a local solution. Okay, so we consider the initial value problem again. So just the same problem we had before. And now we say such that there is some real number R, such that F is analytic on a closed ball of radius R around 0. So that means that there's a sequence so that we have the power series around 0. So some sequence A such that for all Z in a ball of radius R around 0, F is given by the power series. Then we have existence result of an existence result for a local solution. So the following is sometimes known as Cauchy's existence theorem, which just says, so if F is bounded on this ball, this should actually be a closed ball, by some real number M, then the solution exists for at least, so then Y exists and is analytic for at least all T that are less than or equal than R divided by M. And next we want to show how to compute this local solution. And before we do that, so what we do before is we state a few results about computing with power series. So computing with power series. So AM, if AM is some power series, which radius of convergence R, then there are some R and some constants R and M. That bound the power series coefficients. So such that AM is less than M times R to the minus M for all M. And here we can also assume that R is less than 1. Okay, so now also if we assume A is polynomial time computable, so the sequence AM is polynomial time computable, by which we here we just mean, so there's an algorithm a polynomial time algorithm that computes AM in the sense that we get as input A and M, and as output a 2 to the minus n rational approximation of AM in time polynomial in n plus m. Okay, so then one thing we want to do is we want to actually sum up the series, so evaluate the function. So we do this for all x with x less than or equal than half of r, because then we can get so then we can get the following tail estimate. So if we sum up to large n coefficients of the power series, then the remainder will be less than m times 2 to the minus n. And so this in particular means for error less than 2 to the minus n, we just have to choose n larger than n plus log m. So this is the number of coefficients that we need to make the error small, and then we also have to approximate all the coefficients and so on accordingly. But it's quite easy to see that well, polynomial approximations suffice. So we can do evaluation in polynomial n plus log m. And similar, I will not show this, but the similar is we can evaluate this derivative for x in the same domain, also in polynomial in n plus d plus log n. Okay, so those are some results we need about computing with power series, and now I will show how to compute the local solution. So now we assume we are given the sequence, we are given the power series. And we know those bounds. And the right-hand side function is just what is given by the power series. So then by this theorem we called Cauchy's existence theorem, we can show that there is there's a unique y such that it solves the initial value problem. And here we can choose t as less than. So we can use those. We can use this this approximation to get an upper bound for the function for any so if we restrict to values that are smaller than r, and we can make it a little bit smaller, then we can get some upper bound that is 2m, and then we can use this Cauchy's existence theorem to show that we can that there's a unique solution in this interval. And what we want to do is use the previous result about evaluating power series to evaluate yt for t that go half the distance. So this is what we call computing the local solution. So computing on this small interval. Okay, I think I will start a new slide. And the idea how to compute this. We define a sequence of analytic functions that give us the power series coefficients for the solution, so such that fm yt is exactly the power series coefficient of the solution at t. Because then we have that the solution is given by this power series. And since we are only looking at initial values at 0, we can just say that this is given by fm of 0. We further know that the solution only takes values in minus RR for the interval we have chosen. And so for t less than 1. And so by Cauchy's integral formula, from this we get that Bm is, so we get an upper bound on the coefficients for the solution. And then using the previous result, so for the complexity so we can evaluate this basically in time polynomial in n plus the complexity to compute Bm for up to polynomial many coefficients. Okay, so let's check how to compute Bm. So again, what we want is we want to define this function fm such that this holds. And what we do is we inductively define the sequence by saying f0 is just the identity function, and fm plus 1 is 1 divided by m plus 1 times fz times the derivative of fm of the previous function. So why does this work? Well, first, we know that y of t is just f0 of y of t, because f0 is just the identity function. And for the next one, so we can just write the m plus 1 derivative as deriving the nth derivative, and this is exactly fm of y of t. And now, since y is the solution to this initial value problem, we know that, and now we compute this by using the chain rule. And then, since we know that y is the solution to this initial value problem, we know that this is exactly f of y of t. So this is what we wanted to have. Okay. And so now we have to show that B of M is polynomial time computable. And the idea here is that, so we only have to evaluate in 0. So we only evaluate f m of 0. And this gives a finite recursion on the power series coefficients. And well, so we can see that to compute fm of 0, to compute which is em, we just need at most m coefficients from an, from the original power series. So need up to m coefficients from am, and then we just do some simple multiplication and addition of power series coefficients. So if we analyze this, we can see we do it around m cubed multiplications and additions of power series coefficients. Okay, so this was how to compute a local solution. Any questions so far? Okay, probably not. So let's go on with the global solution.
I have a question.
Yes.
What do you mean local? You mean the solution around the 0 or around any? The t is given, right? So around the t.
What is p?
I mean t the time.
Oh yeah, t is so t is given. T is given, and t is less than t. So t is given and t is less than.
Okay, I see. Thank you.
Divided. Okay. Did that answer your question?
I'm not sure that t is bounded by some value, but how small is that? Could we compute when t is like large enough, or could we compute for arbitrary t?
So I will not, so the next thing, so this is just the first step in the algorithm. So the next thing will be to extend it. So this can be, well, it depends on, so it depends on the, so it can depend on the function. It can be very small, it can also be large.
I see. Thank you.
Okay. Okay, so let's see how we can extend this. So the assumption here is that f is from the unit interval to R is analytic. And for each point in 0, 1, we have access to the power series around this point. And we have a global bounds for all of those power series. So this is an assumption we make, but this is actually, this is usually not so hard to get, because we can, for example, if we have the usual function space representation of f and have some upper, so know that f has an analytic extension to some rectangle in the complex plane, and we have an upper bound of this f, then we can get those the things I've written down here. And we assume that there's this, so when there's some solution from 0, 1, that solves the initial value problem. Then we can just, so what we can do is we can stepwise, so we can use this local solution algorithm to get to stepwise, so to iterate it stepwise until we reach any point. So we can compute it by stepwise running the local algorithm. So, sorry, that was a little bit fast. And so what I mean by this, so we can start, so we are given, so we start with the power series given at the initial value. We start here, then use the series to compute the local solution around this, then make some small step. So make a small step of size r divided by 4m, and then use. So then we get a new solution y1, and we use this as a new initial value. And then if we need to make any of the intermediate values more precise, we can just increase the number of power series coefficients that we look at. So this works when so this only works if all the intermediate values we need also we will only need with polynomial precision. So what will happen is, so we have, so instead of giving the algorithm for the local solution, so it will start in 0, but then we will only get, so instead of, so y1 will only be an approximation of the real value y of t1. So what we still have to show is that it suffices to approximate, so that this distance is enough to be 2 to the minus poly of n. And this is what we want to do now. So this is true because there's some continuous dependency on the initial. So we can quantify the continuous dependency on the initial values. So we have the following theorem, which is, so this is sometimes, so this follows basically from the more known theorem, which is known as Grünwald's lemma. So what we have is that if f is L Lipschitz and y0 and z0 are two different initial values for the initial value problem, y dot is f of y, then if y, the distance between yt and zt from the distance of the solution functions at any point t is less than the distance of initial values times e to the lt. And so from the constants we have, so since we know that am is less than m times r to the minus k, we actually get a Lipschitz constant because we can bound, so we can use those constants to get a bound on the first derivative, and from this we can get a Lipschitz constant. So we actually get, we get that the function will be Lipschitz continuous with Lipschitz constant less than or equal to m divided by r. So this means if the error at step I is less than or equal than epsilon, then if we compute the exact solution using this wrong initial value, so using this slightly wrong initial value, that's the epsilon wrong initial value, and compare it with the true solution at the next point, this will be less than or equal than epsilon. So now we just insert those constants here. And we get that this is actually less than. So this will be, so this is 1/2. So this will be less than 2 epsilon. So the error at most doubles in each step. So in total, we get that we need to do all if we do all intermediate approximations with precision 2 to the minus n plus the number of steps we do, then the error will be less than 2 to the minus n. Okay, and that's the algorithm. Any questions so far?
I have a question.
Yes.
If f is known to be Lipschitz,
yes,
should we also know L in advance?
You mean if we want to use this p-space algorithm?
I'm actually concerning about whether my work last week is applicable to calculus. So I am concerning about your
Yeah.
functions.
So even if we want to do some simple algorithm like using the ODE rule, so the ODE rule because we need exact error approximations, right? So even if we use the ODE rule, we need we need some additional information. So for example, if we usually the ODE rule is set to converge linearly if it's 2 times. So if if the solution is 2 times continuously differentiable, right? And so to make this algorithm actually work in this time, which will still be exponential time, because it will need exponentially many steps, but we will need this additional information to get the error bound.
I'm not concerning about complexity, but I'm concerning about computability.
Yeah, even for computability in this very general setting. So if we are thinking about the input as a function, so we need some additional information. So it's not enough to just be able to evaluate to approximate the function.
So you are basically computing a functional, right?
Yes, yes. To compute a functional, which means that the function itself will be an input, we need some additional information. Mm-hmm. Okay, did that answer your question? I will assume this is a yes. Okay, so the rest, so this was the whiteboard part. So I will now actually start the slides. Okay, so what we just discussed already a little bit is we can also put this into the framework of representation. So really talk about computability of the operator. So that means we have to specify the representation. So basically, have to specify how to encode analytic functions. So one possible way is we can get such a representation for analytic function that are analytic on some rectangle. So if the function f is analytic from -1 to 1 from -1 to 1, then there will be some complex analytic extension to such a rectangle, like you see below, and then we can instead of encoding those parameters m and r, we can just instead encode some integer parameters, which is one is this L, which is basically the radius of the power series, and an upper bound of the function on the rectangle. And we can also extend this to multivariate analytic functions. So for multivariate analytic functions, the main idea is that we can reduce all operations to power series in one variable. So instead of having, so the bound will look like what you see. Can I actually? I think I cannot draw anymore when I'm in presentation mode. That doesn't matter. But anyway, so you will have a bound of the form as you see on this slide. And then we can, for example, reduce evaluation of two-dimensional power series by first evaluating a one-dimensional power series, which will give the coefficients for the next series, and do this iteratively. But it's important to note that the complexity of all operations will grow exponentially in the dimension. So this doesn't work very well for very high dimension. or even for not so high. So it doesn't even work very well for intermediate dimension. So this is why I want to look a little bit about how to actually implement this. So of course, this can be just implemented straightforward by just implementing all the data we have in some exact real computation framework, such as IRAM, where we then would just have a C++ data type for analytic function, which contains, for example, the power series around some point and those additional constants. And then we can define just as in the theory, operations for addition, multiplication, derivatives, and ODE solving. But this is usually not very efficient, especially if the dimension is higher, because so the problem is that we have to be very careful about how many. So we will need quite a lot of power series coefficients quickly, and this breaks the efficiency very quickly. But there are many ways how to improve that. So as a few things I tried is that instead of actually operating on power series, is encoding most of the standard functions in some different way, so that we can compute the derivatives of them, and then just use tools like automatic differentiation techniques on those standard functions, and so that we can compute higher order derivatives much more quickly than using the power series itself. So in experiments, this worked much better. And of course, there are also some other ways some smaller things that can lead to quite a lot improvement in efficiency. So for example, so what Norbert tried a lot is using Taylor models, and I tried something similar with affine arithmetic. So some ideas from interval computation can be used to improve the performance significantly. And one last thing I want to talk about is what I'm working on more recently with Florian, is how to formalize such things and prove them correctly in COG. So I gave a talk on this a month ago. Maybe some of you were probably there and some others were not. But so I will not really talk about this library Florian is writing in COG at the moment, but just say that there's this incon library, which is a formalization of computable analysis in COG. And in this library, we have, for example, the notion of a represented space similar to what is common in computable analysis. So here we can represent abstract spaces, like this abstract base type could, for example, be the real numbers defined in COG, or some analytic set of analytic functions that is defined with respect to the real numbers in the standard library in COG. And then we can, then we define names of such a space by defining countable types of questions and answers. And a name in this, so a name is then just something which we can ask those questions and get some answers. So in this way, we can also encode analytic functions. And we started a little bit about formalizing some results about power series in incon. For this, we used another COG library, which is called Coquelicot. So this library is a library that contains many classical mathematical statements about power series, limits, and sums. So just doing classical mathematics and no computability, no results about computation. So no constructive results, but just classical mathematics. And then we defined a representation for power series in incon, which looks like this. So we define the set of power series with radius of convergence larger than 1. And then we can define such a bound, which is a bound similar to what we have seen in the algorithm in the talk. So just some integer constants a and k that bound the power series coefficients. And then the representation is given by the by the series itself and about this bound. And then we can define all these operations in a uniform way. So we can define, for example, so I think we have started defining just the simple operations like multiplication addition, and so on. And then but we could also define, so a next step would be to define ODE solving. So this is the end of the talk. So let me come to the conclusion before I will look at the chat if there are some more questions. So I presented a simple exact ODE solving algorithm based on power series. There can be made many further improvements for practical applications. So some things we want to do in the future is implement and verify this in COC, which will also require to first prove some classical mathematical facts about ODEs that are not available that we haven't found in any COC libraries so far. And well, one interesting point would be if we could somehow extend the results of ODEs to some form of to some results on some form of partial differential equations. Okay, this is the end of the talk, so thank you very much. Are there any questions, comments, remarks, or anything else?
I have some additional question.
Yes.
If F is computable, that means there is a Turing machine equivalent to F, right?
There is a Turing machine that yeah. So it means there's an Oracle Turing machine that computes F. Yeah.
If F is known to be computable and continuous, is it possible to computably determine whether it is differentiable at certain point?
No.
No?
I don't think so, no. Any more questions?
I have a question. In the the computing from the local answer, the local solution algorithm, you assume that the Y is analytic so that it has a power series expansion at zeros, and the coefficient of the power series is that computable from F, or do you assume that
it's not computable from the standard, from the function space, from a name in the standard function space representation? It is not computable.
So you are assuming that it is also part of the input?
Yes, I'm assuming that it's part of the input.
Thank you. And it seems that if the T is right, your algorithm seems to take more and more time to compute the solution. So in some sense, the time depends on not only the output precision, but also the size of the magnitude of the input.
Yes. So if we take, you mean if we take the time as an additional input parameter? So for this, so when I defined the global solution, this was also only for up to some time that we defined to be 1. But we can of course also take this compact domain from 0 to T. We can also take the T as an additional input.
I see. Thank you for your answer.
And what is the time dependence on that T?
Well, it's linear. So if we, but of course the function might, so it might get more complicated. But if everything else stays the same, then it's just linear in T, because we just need to make more steps.
And practical efficiency?
Well, all of this, so I haven't really done much for improving the practical efficiency, but the just a straightforward implementation of the theory it's not very fast. Let's say like this. Well, it's okay for one-dimensional functions, but as soon as the dimension grows quicker, then even computing on a very small domain will take lots of time, because all of those operations are so all of the operations on analytic functions are exponential in the dimension. So if we just evaluation of some three-dimensional function will already be something of cubic complexity, I think. So even though it's still bounded by some polynomial, this polynomial will have a very high coefficient.
So practically, even in the two-dimensional case, it works very slow, right?
So I think for the two-dimensional case, it can still be made. It's still okay, but well, it depends on what you mean by okay. But it's still not very efficient. But you can still wait for the result, I think. So at least this is what I remember from the experiments that I did 2015. So I'm not sure if this is true.
Okay, you think it can be improved in the multidimensional case?
Sorry?
Do you think it can be improved?
Well, I'm not sure if it can be improved in the very general case of analytic functions, but so in practical, in the implementation, it made a lot of sense to define standard functions like polynomials and also sine and cosine, and then have some special properties for which we don't really need to compute all the power series coefficients. For example, for polynomials, we know that the number will be bounded by the degree of the polynomial, so it doesn't make sense to go very deep into the power series. For that, it was much faster. So for polynomials, it was actually quite okay. Well, yeah, so it was at least much faster than for general analytic functions.
Okay, thank you.
I'm not sure how to improve it for the very general case when we are just given the power series, because then, well, there's not much hope that the dependency on the dimension will not be exponential, right? In this case.
I see.
And also for small precision, it makes sense actually not to use this method, or at least combine it with some method which will decrease the step size. So in this power series method, the step size is somehow constant. It only depends on the function, but doesn't depend on the output precision we want. But it can make sense to combine this somehow. So we can also, instead, to get higher precision, can make the step size smaller and keep the number of coefficients constant, which will, well, asymptotically, this will be exponential time, but still for not so high precisions, this sometimes works better than increasing the number of power series coefficients.
Okay.
I have some more questions. All your algorithms are deterministic, right?
Yes.
If we also concern about probabilistic algorithms, could we apply it to loser conditions?
This is a very nice remark. So well, it's a little bit hard to make. Well, we have to think about how to make this precise, right? But there might be some way to formalize this, and then. So the question is, well, what exactly do you mean by probabilistic? So it should still give the exact result, right? Or you mean just give the exact result with some probability or something like that?
As I said earlier, I want to apply my last week's work to calculus, but as you said, it is impossible to determine whether a function is differentiable at arbitrary points. So what if we could ensure whether it's differentiable to
Well, actually,
probability?
But so in today's talk, I even assumed that all the functions, that the input that we only have analytic functions as input. So I already have the assumption that it's differentiable.
Sorry about off topic here, but it's so